This video lesson is about motion, the way that I teach in classroom. The video content, I talk about the worksheets that I use to take notes, motion terms and definitions, motion equations, and strategies to solve motion questions, and also apply for labs, vertical motion downward, with diagrams and main features, also for vertical motion upward, for horizontal launch, and projectile motion. This video lesson is about kinematics, a section of physics that explains motion of objects without reference to the forces which causes the motion. You may copy this form to take notes as you watch this video. In this page, I will introduce motion equations. I will explain horizontal and vertical motions. And in this page, I will explain horizontal and projectile motions. Both pages make a useful foldable for your reference as you solve various motions questions. Let me start with some important terms. Distance is defined as how far an object goes from a reference point. The unit for distance is meter. Its abbreviation is m. Time. It's defined as how long an event takes. The unit for time is seconds, and abbreviation is lowercase s. Speed is the distance traveled over a period of time. The unit for speed is meter per second, abbreviation m-s. Velocity is speed with a direction. For example, 20 meters per second southeast. Acceleration is defined as the change in velocity over a period of time. So here is the definition in terms of fraction. The unit for acceleration is meter per second square, abbreviation meter per second square. Now let me talk about motion equations. And I will start with the acceleration formula to derive the first motion equation. So here I have acceleration is the change of velocity over time. And we know the change of velocity is the final velocity minus initial velocity. Doing the substitution and rearrange this equation in terms of the final velocity, here is our first motion equation. Final velocity is equal initial velocity plus acceleration times time. Now equations 2 and 3 are derived graphically and are written as follows. The second equation is distance is equal initial velocity times time plus half of the acceleration times square. The third equation is the final velocity square is equal initial velocity square plus 2 times acceleration times distance. And the fourth equation for this lesson is velocity is distance over time. Now notice that equations 1, 2, and 3, acceleration is different than 0. So we have terms here with acceleration. But for the fourth equation, acceleration is 0. So when the velocity is constant, there is no change in velocity here. Therefore, there is no acceleration. So then we can use this formula. Okay, so again, the equation 4 can be used with constant speed or velocity when acceleration is 0. Now, to solve motion word problems, we have two steps that we are required to do. One is draw a diagram to represent all the variables involved in the motion. And the second one is set up a table with the SI units for all the terms that we use in motion. For example, here the initial velocity and final velocity, the units are meters per second. Distance in meter, acceleration meters per second square, and time in seconds. Horizontal motion practice problems key terms. Object starts at rest means initial velocity is equal to 0. Object is moving with an initial velocity means the initial velocity of VI is equal to that velocity. Object ends up with a particular velocity means the final velocity is that velocity. Object is moving, then stops means the final velocity is 0. Object is moving, then slows down means the acceleration is negative, is decelerating. So here is the variables abbreviation with descriptions. Vi, initial velocity, V sub F is final velocity, D is for distance, A acceleration, and T for time. Let me start explaining both diagrams below that illustrates vertical motion downward before taking notes of key terms. Please note that on both diagrams, an object, in this case a ball, is falling from a height to the ground without friction. Also, gravity is acting on both falling objects, making them to accelerate 9.8 meters per second every second, which is equivalent to 9.8 meters per second square. I have both diagrams side by side with a hypothetical position AA, BB, CC, and DD as they are falling to simplify my explanation. The left diagram shows an object dropped, which means the initial velocity is 0. On the right side, the object is being thrown with an initial velocity of 10 meters per second. Now, as 1 second has passed by, the new velocity is plus 9.8 meters per second. After 1 second is 9.8 meters per second. And here I need to add 9.8 meters per second to the prior velocity, and now I have 19.8 meters per second, which means after each second the velocity increases 9.8 meters per second because it's accelerating. Again, on the right side, I have to add the 9.8 meters per second to its previous velocity, which is now 29.6 meters per second. And when the object is dropped for the same position, I have 19.6 meters per second. Now, the last time, I'm going to add 9.8 meters per second, and the velocity the ball is going to hit the ground for when it's dropped is 29.4 meters per second, and when it's thrown with initial velocity, in this case 10 meters per second, is going to hit the ground with a final velocity of 39.4 meters per second. In both situations, the object will hit the ground with a higher speed as both accelerate over time. Now you are ready to take notes about the key terms for vertical motion downwards. Number 1. Object falls from rest means its initial velocity is 0. Number 2. Object is dropped means its initial velocity is also 0. Number 3. Object falls and velocity is not mentioned in the question. Assume its initial velocity is 0. Object is thrown downward with a velocity means the initial velocity is that velocity. And the last one, all falling objects accelerate with an acceleration equal to 9.8 meters per second square, regardless its mass. Important note about vertical motion. When solving vertical motion problems, use the following abbreviations to minimize the number of variables involved in motion, and use the data table for all types of practice problems. Make A acceleration, not G. Make D the height, not H. Vertical motion is straight upwards. This diagram shows the trajectory of an object. In this case, I'm using a ball from straight upward. I will explain separately the path of the ball as it goes up and then comes back down. Then I will explain the key terms for upward vertical motion. Now let me start with the trajectory when the ball goes straight upwards. At point A, the ball is thrown straight up with an initial velocity greater than 0. It's moving against gravity. At point B, as the ball goes up, its initial velocity decreases due to gravity acting against this motion. At point C, the ball velocity is almost 0 and about to stop. At point D, the ball finally stops. Its final velocity is 0 and it has reached its maximum height. Now let me explain what happened with the trajectory when the ball is coming down. At point P, the ball is falling back down as a free fall, which means its initial velocity is 0 and the ball is accelerating at 9.8 meters per second square. Remember, every second is going to pick up 9.8 meters per second. So at point C, the velocity increases 9.8 meters per second each second. So if it is 1 second later, so there will be 9.8 meters per second. At point B, the velocity is even higher than at point C, plus 9.8 meters per second. And at point A, the velocity reaches the same velocity as when it was thrown upwards. Summary. At point D, as the thrown object goes up, it decelerates and stops. So the final velocity going up is 0, and the object has reached its maximum height. Also at point D, as the object goes down, the initial velocity down is 0 and it accelerates with an increase of 9.8 meters per second each second. The thrown velocity is always greater than 0, which means at point A, the initial velocity going up is greater than 0. Vertical motion upward. Learn the key terms. Number 1, object is thrown upward with an initial velocity vi up is equal to that velocity. Number 2, when object reaches its maximum height, its Vf going up is equal to 0. Number 3, the velocity of an object going up decreases over time, which means the acceleration is negative 9.8 meters per second square, or in other words, is decelerating. Number 4, when object is coming down, its initial velocity down is equal 0. Now let's learn some important notes about vertical motion upward in terms of time. The time it takes for an object to go up is the same time it takes to come down, which means the T up is equal to T down. Therefore, the total time the object stays in the air is the time in the air is equal time up plus times down. Since both are the same, so we can state that time in the air can be either 2 times times up or 2 times times down. Horizontal launch above the ground. So here we have a ball that is rolling over a table and is going to leave the edge of this table, and the trajectory of this ball is going to be this arc shape. So to explain this shape, I have to divide this motion into two sections. One into the horizontal component, and as I explain the horizontal component of this trajectory, I'm going to build this motion table. So let me start with the velocity this ball is going to leave the table, which is the initial horizontal velocity. And this velocity is going to remain with the same direction up to landing the floor. So the horizontal velocity is not affected by gravity, which is vertical. The horizontal velocity is constant, which means that the initial horizontal velocity is going to be the same as the final horizontal velocity. For this reason, I'm going to label the horizontal velocity at any point of this trajectory VH. So, the initial velocity horizontally is VH, the final is also VH. Now the distance from the base of this table to where the ball lands, I'm gonna call DH, the distance horizontally, DH. Now since VH is constant, the horizontal acceleration is 0, so acceleration here is 0. Now I have the horizontal time that I'm gonna call TH. The horizontal distance can be calculated by this formula. dh is equal vh times th, which is the fourth formula from the motion equations. Now let's take a look vertically. Vertical velocity is affected by gravity. So here is when the velocity is getting greater as the time go by, just like a free fall, which means the initial vertical velocity is 0. The vertical velocity accelerates 9.8 meters per second every second, or 9.8 meters per second square, because of free fall. Now, as the time go by, so this velocity is going to pick up speed and is going to land the ground with a higher value. Now let me complete this table. So the initial velocity for this type of motion is VVI, which is 0. The final velocity is VVF, and the distance is the height from the vertical height where the ball is located to the ground, which is dv. Because it's a free fall, the acceleration is 9.8 meters per second square, and the time vertically is tv. Now, the horizontal time and the vertical time are the same because the components, horizontal and vertical, are together. For this reason, we can simplify the equation to use vertically because the initial velocity is 0, so dv is 4.9 tv squared. Here is how I analyze horizontal launch. I separate both directions. One is horizontal, with the only formula that I can use because acceleration is 0. And the vertical direction. The initial velocity is always 0 because it's a free fall. And the acceleration is always 9.8 meters per second square. When using the second equation, I can eliminate VIT because VI is 0, and this term here, I can divide the 9.8 by 2, and it's 4.9. So now I just need to customize the variables for the vertical direction. Horizontal launch key terms. Time to take some notes. The first one, the horizontal velocity is always constant, which means the initial horizontal velocity is equal to the final horizontal velocity. Number 2, since horizontal velocity is constant, the horizontal acceleration is 0. For the horizontal direction, use this formula, dh is equal vh times th, to calculate any of these variables, distance, velocity, or time. The initial vertical velocity is always 0 and accelerates with plus 9.8 meters per second square. For the vertical direction, use this formula, dv is equal 4.9 tv squared. And finally, the horizontal time th and the vertical time tv are always the same. Projectile motion. Object is launched with an initial velocity at angle. I will start by describing the trajectory of a ball from sideways, forming an angle with an imaginary horizontal line. The previous motions described in this video, I explained all the features involved with a ball from straight down, then straight up, followed by from horizontally above the ground. This trajectory here is commonly known as projectile motion. First, I'm going to explain how to calculate the horizontal and vertical components of the initial velocity in terms of this angle data. Okay, so first I'm going to calculate the horizontal component of VI, which is VHI, and the vertical component of VI, which is VVI. Now I'm going to use the sine and cosine to calculate the value of the components. So since VHI is adjacent of this angle, so I'm using cosine. So cosine is adjacent over hypotenuse, which is VI. So here I have the terms. VHI is equal to VI cosine of this angle. For the vertical one, so I'm using sine because sine is the opposite, which is VVI, over the hypotenuse, which is VI. So here I have the function, the expression that I'm using to calculate VVI, which is VI sine of this angle theta. Horizontal analysis. The horizontal velocity Vh is not affected by the vertical acceleration of gravity and will remain the same value and direction the entire trajectory as it goes up and comes down. The horizontal distance, dh, is measured from where the ball is launched to where it landed at the same height level. The horizontal time is the time the ball stays in the air, and it's equal to the time up plus time down. So the time in the air is the sum of both times, which are the same. So we can also write or calculate the time in the air is equal to 2 times the time up or 2 times the time down. Now for the horizontal table, VI is VH, VF is VH because it does not change. The distance is DH, the acceleration is 0 because velocity remains the same, and the horizontal time is the total time in the air. Vertical analysis of a projectile motion. So the initial vertical velocity, VVI, is when the ball is first launched, and as it goes up, the velocity decelerates due to the gravity acting against it, and it stops, and now it starts to accelerate and land on the ground level. The maximal height, dv, is when the ball stops before changing direction. It's important to notice that the projectile motion has two sections, one going up and one coming back down. Now, the vertical time, TV, is the time it takes for the ball goes up. Because of the symmetry of this type of motion, we can state that the time the ball goes up is equal to the time the ball comes back down. We are neglecting friction the effects of the wind, and other external factors. So we can state the time the ball goes up is equal to the time goes back down. Now for the vertical motion table, we are going to make some adjustments. Number one, this table needs to be going up. So as going up, the initial velocity is the vertical component, the initial vertical component that we need to calculate in terms of the angle. The final velocity that goes up, is going up, is 0. And because it's decelerating, so our acceleration of 9.8 meters per second square is negative. I have explained a detailed analysis for each type of motion separately: straight downward, straight upward, horizontal launch, and projectile motion. Please watch this video again. Draw all diagrams and take notes of the main features of each type of motion. Thank you for watching.